this video, we're going to look at graphs of exponential functions and kind of apply what we've learned from previous graphs to these. So we're just going to start with a basic graph here. We want to graph 2 to the x. So I'm going to go ahead and we're going to just do old school, plug in some values for x, see what we get. So we'll go ahead and figure that out. And let me go ahead and make a little place to graph over here. All right. So let's go ahead and plug some values in for x. I always usually like to start with the basic 5 when we're uncertain, which would be the -2, -1, 0, 1, and 2. Sometimes I start with 0 and then do the 1 and 2 and then jump back to the negatives. But since we're kind of planning this, those are usually the 5 I like to start with. Okay, so if I plug -2 into the exponent, remember what happens is that flips. So here, just to refresh, that's going to become 1 over 2 squared, which is 1/4 or 0.25, right? If I plug in -1, that's going to become 1/2. If I plug in 0, anything to the 0 is 1. If I plug in 1, that's going to be 2. And when I plug in 2, that's going to give me 4. Okay, so here's what we're looking at. -2 and 1/4 would be like maybe here, right? And then it goes to 1/2 here at -1. At 0, it's at 1. At 1, it's at 2. And then at 2, it's at 4. So this is how the graph is kind of looking. And what's going to happen is we plug in bigger values, that thing's going to shoot off. But as we plug in smaller negatives, they just give us more and more fractions. So what we have here is a horizontal asymptote. So we have a horizontal asymptote at y equals 0 because there's no value I can plug in for x into the exponent that's going to all of a sudden make this thing negative. So this thing is never going to hit the negatives. It's just going to keep getting closer and closer to the x-axis. Okay. So let's see what happens. Let's do another graph. Oops, below here. Let's do 1/2 to the x. Okay, 1/2 to the x. We're going to kind of just take the same exact approach. I'm going to plug in -2, -1, 0, 1, and 2 and graph it. And just like a moment ago, I don't really need to worry about negatives. 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So I don't really need to worry about negatives since this isn't going to all of a sudden become a negative based on plugging something in for the exponent. But when we plug a negative exponent in for something that's already a fraction, the whole fraction flips. So it's 2 over 1 to the +2. So that's going to become 4. And then if I plug in -1, that's going to become 2. If I plug in 0, still going to be a 1. If I plug in 1, it's going to stay 1/2. And if I plug in 2, I'm 1/2 times 1/2 is 1/4. So it's similar values as the last one. They're just kind of in reverse order. So what we have here is actually kind of a reverse of the graph we have above. Oops. That should have been starting at 4. There we go. Then to 2, then 1, then 1/2, and then 1/4. So we still have a horizontal asymptote at the x-axis, but it is going the reverse direction. So what we're seeing is this thing is decreasing as it goes, whereas the other graph above is increasing. Both graphs, by the way, are concave up since it's cupping upwards. But there we go. There's our graphs. So let's sum up what we'll see when we kind of look at these exponential functions. So graphically, we would be graphing something in the form f of x equals a times b to the x. So a being that it's some sort of multiple that could be in front. So a is the vertical intercept of the graph. All right. B determines how the graph grows. So if B is bigger than 1, like when it was 2, the graph is going to increase. When B is less than 1, or a fraction like we saw in the last one, the graph is going to decrease. The graph will have a horizontal asymptote at y equals 0. We saw that in both. And then the graph will be concave up if A is bigger than 0, meaning that number in front is positive. And in our previous examples, we had no number in front. So the number in front was quote unquote 1. All right. And if A happens to be less than 0, it's going to end up flipping the graph and being concave down. All right. And then the domain for all of these is all real numbers or negative infinity to positive infinity. And the range, though, is never negative. So it's going to be from 0 to infinity. And we don't include 0 because it just keeps getting closer and closer to the x-axis without ever actually achieving 0. We just get smaller and smaller fractions forever. So that's kind of the basic breakdown for exponential functions. Now let's look at some examples where we have graphs and we're going to kind of play the matching game here. All right. So what's nice is we have two distinct vertical intercepts. So here we have 2, whereas here we have 4. So I already know that the best contenders for f of x and g of x are the ones that are crossing through 2 right here. And then the ones that are crossing through 4, h of x and k of x, that's the best contenders right there. Okay, so actually, I want to focus on h of x and k of x. I think those are the easiest to tell the difference between, because this one is going to be increasing in value since it's bigger than 1. But this one, since it's smaller than 1, is going to be decreasing, like our 1/2 function. So this is going to be k of x. The one that's decreasing is k of x, leaving the yellow one that's increasing to be h of x. Okay, so that leaves the other two functions, and what we see is that one is increasing at a faster rate. The green function is increasing at a faster rate, and when I'm comparing f of x and g of x, 1.8 being a bigger number means it's going to be increasing faster. So this will be g of x, leaving the blue one to be f of x. So there are some examples in the homework where you kind of do this matching game based on these characteristics. Okay, now we do have transformations, all right, for exponential graphs, referring to like the vertical and horizontal shifting, and maybe even some sort of stretching across or flipping across the axis. So let's say we're going to work with the original function is f of x equals e to the x, and it's a vertically stretched by a factor of 2, flipped across the y-axis and shifted up 4. Okay, so how's that going to look? So a vertical stretch is always multiplied in front. So we have a vertical stretch of 2. And since it's flipped across the y-axis, that makes it negative. And shifted up 4 units, that means we're adding 4. Oh, I just realized if it's flipping across the y-axis, negative is not going to be in front of the whole thing. A negative in front of the whole thing shifts it, flips it over the x-axis. The y-axis flipping happens when you put a negative in front of the x value, not the y value. So that's where the negative is actually going to be. All right. So let's look at an example of a graph based on the 2 to the x that we did earlier. And if you need to refer to that graph, that's fine. I'm going to I have it somewhat memorized, so I'm going to kind of know how that graph somewhat works based on memory here. Okay, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now, I do see that they're minusing 4, so we're going to be shifting downward. So here we're going -5 there. But on the y-axis up here, I'm probably going to go a little bit higher. And the reason is I have it stretching quite a bit by a multiple of 3. So I at least want to get myself some space. Let's see, that's 4, 5, 6, 7, 8, 9, 10. So I'll go up to 10. So 5 everywhere else, 10 at the top. Okay. So my original graph, when you plugged in 0, you got 1. All right. But because we're shifted down 4, we're going to actually start not at 1, but at 0, 1, -1, -2, and -3. So here's where we're actually going to start. Now, normally we have a horizontal asymptote at the x-axis. So that's going to shift down 4 to be right here. So I'm going to kind of draw this dashed line to represent the shifted horizontal asymptote for me. Okay, now in the original graph, at 1, it was at 2. Okay, so when I plugged in 1, I was at 2. But since that's shifting down 4, I'm technically kind of here, but then I have a multiple of 3. So I'll deal with that multiple of 3 in a second. So how about I just start by shifting down 4? Okay. And then at 2, it went to 4. So that would be mimicking what it would be like at 4. And then this value was a half and then a fourth. Okay. So this is what the graph would look like just shifted down 4. Now I'm going to stretch it by a factor of 3. So basically, each value then is going to go times 3. So instead of being at this value here, I'm going to be multiplying it times 3. So let me be clear. When I'm saying times 3, I'm talking about like envisioning that this is the 2 to the x graph and pretending that this is my new x-axis. So times 3 means I'm really going to be looking at it starting here. All right. Then I would be taking this point, which would have been at 2, 1, and it'd be at 2, 6 instead. So I'm going to go 6 up from my fake x-axis. So 1, 2, 3, 4, 5, 6. So this is the new point. And then instead, this particular point was the 0.24. So 1, 2, 3, 4. That's that one. If I'm going to be moving it up by 3, 4, 3 is 12. So let me count out to 12 then. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So there's where that will be. Now, my half value here, right there. Oops. If this had been a half, right? And that, when we're multiplying it by 3, becomes 1.5 from my fake x-axis. So 1.5 is going to land me right here. And 1/4 would become 3/4. So that one's actually barely going to move. All right. So here is my new stretched out graph. Now, you are able to, of course, plug in some values to verify. But if we're talking about the transformations, they're kind of wanting us to think about using those to graph the new equation. But you could always double check by plugging in values for x. In other words, plug in the big 5 values and give it a shot and see what you kind of end up with. That's always a safe bet when we look at graphing. So let's kind of sum up the transformed version of an exponential. And they like to make a note that y = c becomes the new horizontal asymptote. And our vertical asymptote is based on both C and A. In other words, if you add those two together, that becomes our vertical intercept. I'm sorry, I said vertical asymptote and I meant vertical intercept. So in our example up here, that was 3 and -4. If you add those together, that gives us -1, which is our green graph is the final graph. And that's where we ended up crossing on the vertical axis. Okay, so let's go ahead and find an equation for the graph shown. Okay, let's start by kind of figuring out some basic information that's easy to identify. So first thing I'm noticing, this looks like that's where the horizontal asymptote is. So our horizontal asymptote, y equals 5. Okay, so that's telling me then that C in that equation up here, right here, f of x equals ab to the x plus c. Here, let me write that down there. That's what we're going to use for this. Equals ab to the x plus c. Okay, so c is 5. Nice. All right. And we could probably figure out some information if we plug in the right things. So here, let me go ahead and I'm going to plug this into the equation really quick. I know what c is. It's 5. And I could probably figure out a pretty quickly since this is crossing at 2, right? That's our y value, 2. Here, let me plug that in, 2. And that's happening when x equals 0, right? That means that b to the 0 is 1. And if I subtract the 5, a is -3. That makes sense because -3 plus 5 will give us 2. So we've just figured out A and C. So f of x equals -3b to the x plus 5. Okay, so now all we have to do is figure out b. So let's pick another point, a nice point that's easy to pull off the graph, and then we'll use that. So I see a couple contenders. I see -1, 3. That's a good contender. And I see 2, -2. I also think that is a good contender. I think we'll go ahead and go with 2, -2. The reason is that's going to give us a positive exponent. So let's plug in. So this is going to equal -2 when x is 2. Okay, so let's solve this. Let's minus the 5 from both sides. So that's going to be -7 equals -3 b squared. Okay, and then dividing by -3 is going to give me positive 7/3 equals b squared. And then I'm going to take the square root of both sides. And plugging that into the calculator, I'm getting 1.527, which I'm just going to round to 1.5. So at the moment, I have f of x equals -3, 1.5 to the x plus 5. Now, I could verify that by plugging in the other ordered pair and making sure it works. So the other ordered pair was -1, 3. So if I plug -1 into here, I get -3 times 1.5 to the -1 plus 5. Okay, so let me plug that in my calculator. So 3 times 1.5 raised to the -1. And then plus 5, I'm getting 7. There, that didn't work out. Oh, I forgot the negative in front. Just kidding. See, kids, teachers can make mistakes too. There, it came out to 3. See, when you plug in the negative in the very front, that helps. Yay, so that was it. It does work. That equation works out nicely. And there we go. That's how we can find the equation from the graph.